Next paper is entitled as Uploadable iSCSI Initiator by Alistair Crooks from the NetBSD Foundation. So please get started.
Good morning, everybody. Welcome. Can everybody hear me? You can't hear me? Can you wave your hands, please? This one's for absent friends. This is the agenda for today's talk. We're going to see how iSCSI works, first of all. I'm going to talk about a bit about portability as well. The design of the portable initiator will follow that, and then we'll look at some of the concerns that are out there in the world about iSCSI. I'll attempt to allay any concerns you have about iSCSI, and then we'll go into some uses for it as well, so you can see what we can do with it, and why some of us think it's quite neat and others are still a bit wary of it. This one. The component overview, really. SCSI protocol over TCP/IP is just basically a SCSI extender. So you can actually run it over the internet, and the iSCSI protocol itself is split into two parts. First is a target, which sits in the device, just the same as any ordinary SCSI device that we have. The second part is the client, which is also called the initiator, and that's what we use to talk to the target. It's altered in with blob storage. There's absolutely nothing there on a file system level, so we don't have any permissions, we don't have any path names or anything like that. All we're doing is asking for a block number and receiving it. The iSCSI target overview. We've had an iSCSI target in the NetBSD world since 2006. It's portable to POSIX systems. It's also portable, and I'm going to end up in a nasty place for this. I've also ported it in my spare time to Windows XP. There's absolutely no hope for me whatsoever. There is a port being made of this. It's in the FreeBSD ports collection. It's also in package stores as well. It's found its way into the FreeNAS distribution, and you should see some of the bug reports I get from there. Very interesting, some of them. Unfortunately, we haven't managed to make it into the OpenBSD world yet, so if any of you OpenBSD people out there would like to get in on the act, please feel free. It's completely portable to POSIX systems. This is the target we're talking about. The target is in the device end, like I said. It receives a request and it sends the responses. Completely dumb beast. It sits there and does the work. I registered NetBSD as a vendor with T10 for the people who do the specs for the SCSI world, which means that we can actually use the NetBSD string in the target and the initiator, which is important, as we'll see later when we do the IQN, the Internet Qualified Name that SCSI uses to do its internal naming schemes. Right. The initiator now. It's used to access the storage on the target. It issues requests, and it receives responses from that target. It appears to the OS as a block device, and you can put up a file system on top of that block device. So we can run NTFS if they're on there if we want, or we can run FFS, any kind of thing at all. The block device itself, it doesn't matter what storage you put on top of it. It could be anything. It's completely agnostic to the idea of the file system. And that is quite a powerful idea as well. Right. Traditional iSCSI initiators. You get these from many vendors, Sun, HP, IBM. Most of the people out there who have initiators have written them all in this way as well. The UNH ones and the Cisco ones the same. It's independent of the target, because the target somewhere far away. This is deep down part of the operating system. It doesn't matter what the targets look like, and it doesn't matter how the target's implemented as well. If you do put the initiator in the operating system, there are certain challenges that we have. One's authentication. We've seen from the PPPD how well that sits, having authentication sitting down there in the kernel. Sorry, I'll put the automatic time on here. Also, security is another interesting challenge too. How do you do IPsec with encryption from within the kernel? Interesting one. And also encryption itself. If we're going to encrypt some of the things, and we'll come on to this later as well, if we're going to encrypt some of the traffic that's going over it, where does that get done? I've outsourced this to my son to do, which is why this is done in open office and not in something else a bit more unusual. And so this is a typical, I don't know if you can see it, it's a typical typical picture of how the initiator works. It comes down through the kernel to the initiator, out across the internet, over to the device, back this way up to the device switch, and back to the blob device. Now there are two ways we can look at doing portability. Right? So let's take the analogy here of moving a house. Right? There are various ways to move a house. This is one of them. Right? And so that's picking up the house and moving it. We don't all do that. Some of us do, but we don't all do that. This is the other one. This is an interesting one. It's a picture of Anthony Charles Winton Blair's house being moved out to number 10 Downing Street. What a pity. Right. Out, definitely. Okay, let's come on to some fuse issues. The reason for showing these right now will become apparent later on. Okay, I don't know if many of you know about Fuse, but it's a file system written to be portable. It sits in user land, and if you came to Anti's talk yesterday, you'd have heard a few things about Refuse, which is NetBSD's re-implementation of it under a BSD license. The main thing is that you set up a whole number of callbacks, and you actually instance these callbacks by calling Fuse main. Fuse main itself will fork and attempt to, let's see, sorry, it attempt to use fuser mount if you're under Linux, or if you're running a FreeBSD, it'll attempt to use mount fuse FS. That's to make sure that the kernel module is there, so that it fixes up various other things as well, and then just exits. What it does is it forks in order to exec that program. And this is from a library routine, so sigh. And you'll be pleased to know that size isn't everything. Feel free not to laugh. Okay. The initiator structure itself, I'm going to come on to it and talk about that. Our iSCSI initiator is threaded. There is absolutely no point in having a single threaded initiator, because then you wouldn't be able to issue multiple requests. You'd have to wait for every request to come back and be serviced. With a threaded initiator, you can send one off, another thread comes in, does another one. Under NetBSD, what we do is perform discovery first. And again, I'll explain all these terms later. And you'll see some of them working too. It then builds a virtual directory tree of that up on the host. Calls fuse main to mount the tree. Sorry, it calls the calls to read and write are then rerouted across the internet to the target. Hold on. The trouble with that is that we fork after creating the threads. Behavior is therefore undefined. Yeah. The interesting thing is under FreeBSD 6.3, you get a core dump for no reason. You just have to get a core dump. You've got to ktrace it to find out what's going on. FreeBSD 7 is different. It'll just kill itself. Won't do anything, just kill itself. So that's progress, I think. Right. Sorry, there we go. One of the things we had, iSCSI test harness. This is what I used to test the target as it was being developed. It basically verifies the correct operation of that target, and it was added at the same time as that one. Hopefully you can't see these bits out here. It sits at the user level. It issues requests to the targets and receives response from the target. It's just plain dumb test harness. It's very much the same as an initiator does, except it doesn't do anything with file systems here. Hopefully you can't see that. Things there. It says file system on it. And let's get this one. So the test harness, all it's doing is sending stuff across the internet to the target. Right, let's take another step back. Look at another of the components we have here. Andy talked about this a bit yesterday. Refuse. It's built on top of puffs and also on top of putter. There's a standardized interface for the user level file systems, and the same API as Fuse. And Fuse runs on those four down there: Linux FreeBSD, Mac OS 10, and Solaris 10 as well. The status of it: it's been in the repository since 2007. It's compilation compatible with Fuse, so we can recompile any of the Fuse file systems and have them work under Refuse. If you want to see more, have a look in package source. There's a whole lot of file systems there: NTFS 3G, AFPFS, NG, and a whole lot of other more unusual ones. Right, the design of the initiator itself. Pictorially, this is what it's going to look like. We have a system call coming down through here, down through the kernel, up through puffs, there, up to lib refuse, back down through there. I'll run that past you again because you probably didn't see it. My hand was in the way. There we go. This is just doing a normal system call, being routed up through lib refuse, back down through the kernel, up to the caller again. To initiator design now. It's built on an existing test harness. We drop the test harness into the kernel. This was the plan originally when we were developing it. The test harness appears as a block device then. We route the file system request to the target, route responses back to the file system, and to do that we were going to extend refuse to work with devices. So what we would be having there is a kind of an analogy of refuse, but instead of working with file systems, we're actually going to be using user-space devices. There's already prior art for this. There's something called FuzzD, I think it's pronounced, or FuseD, which was a BSD licensed user-space device implementation for the Linux kernel. Some of you will have seen my pathetic attempts on mailing lists to interest people in it in something called PUD, which was a pass to user-space devices, and that was extending Andy's thinking metaphor again. Basically, sending refuse to handle devices. So pictorially, let's have a look at this. This one is now with a test harness. So we're coming down through the kernel again, going up through lib refuse, up to the test harness, across to the target there. Back down through the kernel, back up there. People want to see that again? Good. Great decision. So let's go into this, the subject of this talk, Virtualized iSCSI Initiator. We use refuse, or fuse, to the user space devices. Communicate with the target. We do discovery, which is how we find out what devices are actually available to us. We'll read the capabilities from those devices. So that's the size, the block size, number of LUNs, all the interesting stuff like that. Then we'll get onto the meat of things. We'll actually read and write blocks. In practice, though, after the discovery has happened, after you've actually found out what devices are there, you don't do anything except read and write the blocks. What are you doing between the initiator and the target? You found out all the information up front. All you're doing after that is reading and writing blocks. So there's not really that much to do. So let's assemble all the components that I've managed to describe here, I hope. We've got the test harness that I used originally for developing the target. We've got refuse, which we can use not just to do files, but also to do devices as well, like Antti said. If I can go back to something that Antti did in Copenhagen, he told me that when he was developing puffs, he actually used a /dev instance on top of one of his file systems. And that was when I suddenly realized that, yes, we can do user space devices across refuse without having to do any of the extra work involved in user space devices. So, putting all the components together, here we have coming down from VND device, above the storage file onto the device switch, puffs up there, across the internet to the target, back down to librefuse. You're all getting very bored by this now because it's taking so long to do this. I can tell that. Okay, so you've now got an idea of what's happening when we communicate up from the VND, across to the target, and back again. You'll see some of the time that's involved to basically route a request from a packet up from the VND, right across the target and back down again. And we'll go into that later as well. Okay. Talked earlier about fuse, forking. What I've had to do is rewrite the initiator to fork itself. The child does discovery, communicates via pipe with the parent. The parent sets up a virtual directory tree, then calls fuse main. This is all to get around the fact that fuse main will fork in the user space library. After that, at the first connection, once we've forked, you connect to the target using threads, because it's all right to connect using threads after we fork, but just not before. So, what concerns do we have in general about iSCSI? What's there that we can really get worried about? Firstly is device scanning. How do we do it now? Because previously, all the devices were directly attached. Now in iSCSI, they're all over the internet. Could be anywhere. How do we actually find out what's there? And that's something called discovery that we'll talk about later on. Security and snooping. How do you stop people looking at all the contents of the stuff that's in there? And it might not just be going across the network. It might be the stuff on the far end of the network. If that target that's over there on the right was in a colo facility that you don't have access control over, how do you stop people looking at it? Right. There's an existing investment in Fibre Channel that a whole lot of people have. They bought dark fibre off the telcos and they paid a lot of money for that. They really don't want to say goodbye to that. Access to blob storage. Another concern for a lot of people. Like I said, if you've got something in a colo, and one of the stories here was about when Virgin Airways started off, first of all, they rented space in a mainframe from British Airways. There was a court case subsequent to that in the VA were reading all the data from Virgin's reservation system. Settled out the court. Performance. One of the concerns, you saw the way that packets have, sorry about that, so the way that packets have to travel all the way across there. That's a concern for lots of people because you're actually adding a user space component in there where it wasn't in before in the traditional iSCSI Initiator. Finally, stability. One thing you want from a file system or a blob device is for it to be stable at all times. So, let's move on. In practice, what we did once we'd actually developed the Initiator was we tried to test it. What do you think we did? We decided to use build.shell, which is the mate world for NetBSD. Builds the compilers, builds all the tools, builds all the userland, libraries, and builds the kernels. The very first test that we did was to run build.shell on top of the Initiator. And that test completed successfully. Not only did it complete successfully, but the performance of it absolutely amazed me. This is admittedly on a huge, hunky machine at the time, 8 gigabytes, 8-way AMD 64. The final performance was within 0.5% of the native performance without iSCSI. Build shell completed in 4750 compared to 4725. Obviously, cache effects may apply because you have everything there in memory. But the fact that you're with less than 1% of performance to be done in noise. It wasn't, but it could be done in noise because of the time that we're taking. So, let's have a look at the initiator itself. 18 kilobytes of source code. Not many people look at kilobytes, but if you do a directory listing of it, it's interesting to know. It's around 600 lines of code, which is commented, so half of that's the license, obviously. There are various benefits to it as well. Maintenance, but it's small. You don't have to do much maintenance on it. There's not that much to go wrong. Stability of it, once again, it's stable because there's not that much to go wrong. Performance of it, I've just shown you some of the stuff in there. And we also gain portability from it as well. So it's not just writing it for one operating system and then having to hack it into a different one after that. It can be used in anything that's got fuse on there. So we talked about discovery, or I mentioned discovery earlier. The disk is no longer physically attached. We can't scan the bus anymore to find out what devices are there. So we use discovery to find out what's there. The target provides the storage information to it. There are various things to do. You read the capabilities from the target. It tells you this is how much space there is. This is the block size of it. This is how many LUNs I've got. And this is the name of it. In the Fibre Channel world, there's something called the simple name server, which does basically exactly that, right? What I've just said. It says this is the storage and this is how much you've got. iSCSI is something called ISNS, which is Internet SNS, and the Storage Locator Protocol as well, SLP. Right. Now, obviously, I took the easy way out, and I'm not doing a live demo as the previous speaker did. This is on a FibreChannel system, and this is showing it doing discovery. So that one there is giving the username. The -H after there, I apologize to all the IPv6 people. The target and the initiator are both IPv6 ready, but I'm not. Okay, so the -D at the end says do discovery. The targets are available there, and that's the name from 7.0 release system. Talked earlier about Fibre Channel investment, things like that. There's nothing I can do for you, mate. You spent all that money on Fibre Channel. I'm not going to say you shouldn't be using it. Fine, get your money's worth out of it. But there's not really much I can do. I think we've got to realise though that you take a decision at a point in time, and you do the thing that you can for it. There we have $3,400 for a 10 megabyte hard disk. Times change. Move on. Right, access to block storage. Anybody can read or write a block. So, what are the ways that we can do this around it? You can use zoning and LUN masking. Zoning is a kind of hardware masking of all the different targets for things. LUN masking, a bit more in software. But they do basically the same kind of thing. They stop people, certain groups, from writing to different devices. The other aspect of this was how do we stop people snooping on it? How do we stop people eavesdropping on what we've got? To do that, you need some form of virtual private network. You can use IPsec with ESP, or you can use other measures. Right. Can everybody see this? Right. First one there is just running the initiator. Right. Run it in the background, and on the local host, we give it a mount point, which is there at the end. I give a user because we log in using chat. Let's move on quickly after that. The second command there, you can see that the actual mount point is mounted. It's on dev puffs. This is an old one. It's not the new dev puffs, I think. The there's a virtual directory that's created here under the mount point. That gives the target name. Sorry, gives the target name there, target 0, and the host name previous to it. The various aspects of it here: the host name, IP address. That's IPv4, but if it was IPv6, it would come up like that. The product name. These are all shown as symbolic links. They're just the easiest way to do it. The main thing here, though, is this storage file there, which is a virtual file. It doesn't actually occupy any blocks or anything like that. It's got a size of 100 megabytes. And that's the file that we use to access the target from the initiator. Target name down there, that's how you find out where you're going in the NetBSD version here. Uname -A, so you can see it running on NetBSD current from Silver. Security and snooping. Mentioned earlier the colo machines. You don't have physical control of the disk. What are we going to do to stop this? The best thing to do is to encrypt the world device. Various ways of doing this. Each of our own operating systems seem to have their own way of doing it. To see how we do it in NetBSD, and there's a worked example that I'm going to go through later on. That's the URL there. Okay, so my notes here. Once again, run the initiator up the top. See it's mounted on the mount point. We put a BND device on top of the storage file. That's the storage file. That was the 100 megabyte file that we're running. The target's exporting 100 megabytes of storage, and we've got a BND on top of that. Okay, I then disk label that BND. So you can see here, I'm putting it as a CCD, as a concatenated disk drive. We've got there ordinary file system things. And you can ask me about programs later on, why I use fancy colors like an explosion or paint factor if you want. But this is the meat of the thing about using encryption on the vNode. We disk label it, and that was the previous slide you saw earlier. It comes back. We then, you then configure the CGD using AES. We then zero the storage out here. Unconfigure the device. We then configure it using this label verification method. So that just means to tell it that you look at this label to see if it matches the thing. This has a nasty habit of failing because of lack of entropy. So just run it again. That's what this one does. And finally, re-enter there. That's to re-enter the password that we're going to be using with the crypto device. We next go on to dislabel the CGD itself. So now we've got the CGD on top of the vNode. We dislabel that. Offset here is 0. We don't have to offset it anymore. And then that was the dislabel command. New file system on it. I could have used the new physical block logging stuff that we have, except that it's not on this version current from October. So we mount the CDD on /iSCSI. You can mount it anywhere if you want. There's a DF of it, copy a file in there, so copy a kernel, and there it is. And finally the uname information yet again. iSCSI uses. We've seen that the file system we put on the blob storage, it could be a normal FFS, it could be in a CGD, it could be absolutely anything that we want. The remote storage appears locally. That storage file that's there is a virtual file. It's 100 megabytes large. There's actually no space taken up for it. It's a completely sparse file if you want to look at it that way. The uses that we can have for iSCSI, and one of the main ones we'll look at now is virtualization. A lot of the people, a lot of the articles I'm reading out there now, they're calling iSCSI and virtualization the killer app for it. We've got centralized storage. That's an important concept as well, because we can use our normal way of backing up, of protecting the storage's integrity and things like that, you know, raiding it and stuff. We can now have storage in inaccessible areas. You can do off-site backups, which you couldn't do before. Before, you'd have to have used some form of Fibre Channel storage area network for this kind of thing. But the advent of iSCSI is actually bringing that down now, and especially having iSCSI Initiator in the operating system, or even an adjunct to it as well. Finally, one that people might not think of, software distribution. Right, let's take them going backwards first. The normal way of installing an operating system these days seems to be to grab an ISO image from the net, download it, burn it to a disk, install the operating system, throw the disk away. You don't have to do that. You could actually just make it available as an ISO image over iSCSI. If you do that, be careful though. Microsoft Initiator thinks everything that it gets, everything it's told about, is writable storage. So it can't write read-only storage. It can't mount read-only storage underneath it. By making ISOs available by iSCSI, you're only downloading the items that are required, and no CDs need to be harmed in the making of that operating system. Mentioned earlier, it's file system agnostic. iSCSI just doesn't care what it was. It's just serving up blocks. There's strengths and weaknesses to that. This is a screen dump of the Microsoft Initiator, just to show you something different as well, and how we're all glad that we work with BSD. These ones that are highlighted in green, are iSCSI disks. You have to write to them, otherwise you get horrible problems later on as well. How do you tell whether that's remote? How do you tell whether it's local? A bit difficult under that. Under BSD, you can just see it with using the VND device, what it's, which file is backing it. Okay, looks like using it in inaccessible areas. One of the things that Hubert Fire loves to tell me is that NetBSD is used on the ISS, the International Space Station. And this is where the astronauts is doing things up in the ISS, and you can probably see that in the reflection on the helmet. So, good do. I'd like to see you doing programming on a laptop disk that has survived exit through the Earth's atmosphere, into the atmospheric problems of that, and what happens once your bad block starting to multiply. What do you do when you get a head crash when you're up in space? You can't really take it back as in an RMA. How are you going to do that? Another picture of the space shuttle for absolutely no reason that it was there. So as long as we have comms, we can use iSCSI to provide backing storage for us that we wouldn't otherwise get. Apart from inaccessible areas, the other place we'd use is dangerous areas. I think most people have seen speed cameras in their life, yeah? Yeah, that's a speed camera there. And that's one afterwards. Right? There's a marvelous site on the internet called Burnt Gatsos. And it's just, there are about 50 or 60 images of speed cameras that have been either blown up or torched. Great. Right, virtualization. The killer app for iSCSI is commonly mentioned now it's going to be virtualization, especially for the mobility of domains. Apologies for not saying that properly. When you have a domain and you're trying to keep it up all the time, high availability, you can easily move it to a different machine and keep the service running, keep it on the local network, everything's fine. If you've got direct attached storage, there's absolutely no way you can do that, because it won't be able to reach the disk. You need something like a storage area network, you need something that's block device, or at a push, perhaps NFS, but that means that there are other problems that you get with NFS. iSCSI fits this perfectly. Right. Storage for PDAs, we talked about the people in the ISS having that. Perfect solution to digital video recorders. I don't know if any of you have got one. I got one for my Christmas. No space left on it yet. Idea is to have centralized storage. No more sinks also. Because if you have centralized storage, then your PDA will be able to attach to it. You don't have to synchronize the local copy that you have. Right. So, where does the storage go if you have a camera phone, for example, like one of these? Or this is what we did before Bluetooth. Where does the storage go on these two models? I'm not sure about that. Right. I've talked about some of the stuff that we've done. Coming to the end now. Future work. Retro iSCSI hot swapping in RAID 1. The idea behind this is to have a local component of iSCSI and have that with a mirror with something that's on a different continent or something like that. So we can actually do RAID 1 backups. You can do that right now if you want. The only reason I didn't was I didn't do the screen dumps and things like that. We can do that at the moment. We can't do hot swap at the moment, well, not with the RAID frame anyway. You could if you have the right devices for it. What I would like to do is to make that work with RAID frame, and I've been talking to Greg Alistair on that subject. iSCSI booting, another almost definite thing that we need. iSCSI booting, definitely need that. We're planning for it in NetBSD 6.0, which will of course be branched at the end of May 2009. Watch this space. Same for iSCSI cloning. iSCSI cloning is a copy on write. So if you're giving a class or something like that, a lot of people are typing on it. They can all make changes. At the end of that changes, because the changes are copy and write, you can just throw away the changes they've made. You've still got your original thing. And there's a whole lot of little games that we can do like that with iSCSI cloning. We can do copy and write. One of the things we can do if we are doing iSCSI to a remote location is that we can take a log of all the packets that have come in and changed it, so that we have a sequential log then, a sequential log of all the changes that have been made. I can do that in time order, I can do it in disk order, or whatever. One of the other things that I want to do is to make a configuration file for the initiator so that we can actually have the attachment after we bring the machine back up, for example. And of course, as you can see, all the advantages of dropping into the kernel, which I'll be doing later on as well. Nobody's shouting no. Right. Let's go to the summary. The iSCSI Initiator is portable. Used in inaccessible areas, secure storage for small devices, secure storage in co-located sites, which is a biggie for some people. Let's lapse into marketing speak and just say low-cost, easily managed IP SAN. Moving on, virtualization is the killer app. It's file system agnostic as well, so you can put anything that you want on there, and we can use it for software distribution if necessary. So those are the things I talked about earlier, the review that we had. Any questions? RC 3720 from IETF.
When you talked about IPsec to encrypt data stream between iSCSI device and whichever client is used, how do you manage the speed problem if there's a lot of data flowing?
If I got that right, the question was with ESP on IPsec,
yeah.
How do you manage the speed?
The speed. If there's a lot of data flowing, and how fast can you do the encryption? It's,
I don't know. I'll get back to you on that one. Right? It's no worse. It's going to be no worse than any other IPsec.
yeah. Okay.
So, however fast your IPsec is, if you've got offload or whatever. Any other questions? Do you mind if I ask you a few questions? Anybody using iSCSI? Anybody intending to use it? Right. Okay, thanks. If you do and are wanting to talk about it or anything like that, please just give me a call.